Hello, I'm Matthew Nelson and welcome to my demonstration on how to optimize a repayment schedule for multiple loans with different interest rates, different principals, and different times to maturity. We'll be using Microsoft Excel 2011, I believe, for the Mac, as well as a Java extension called Solver. So a very common situation is having many loans that are unconsolidated, and you want to have a goal date of when those will all be paid off at the same time. Well, this is very difficult to do using an amortization schedule or any normal techniques that don't utilize the power of a modern computer. So what we're going to do is set up a solver uh, program that will do all the work for us. So let's get started. So we see here we have 7 different loans, A through G. In column B, we have principal, and C, we have the annual interest rate. I'm going to assume 360, 365 basis. We have the payment column, which is a calculated field, okay? And next to it are our inputs. So this could be any loans. The table is extensible. You could just add rows to add more loans or zero them out or delete them, whatever your situation may be. So the payment will be determined by the solver. So it is a constant that the iterative program will determine, and we do not need to concern ourselves with that. That is the hard part, that we're letting the computer do the work for us. The next column, we have the time to maturity in days, and that will be determined on a calculation based on your inputs below. And the maturity will be equal for all of these because we want to have them all paid off at the same time. In column G, we see the change in days. Now that is the difference between when the loan will be repaid based on the payment in column D and the desired maturity date. So the way the solver will work is if that change in days is 0, well, that means that our goal has been accomplished and we've determined the exact payment schedule that will make all the loans end at exactly the same time. Okay, so a little bit more. Let's look at some of the inputs. Uh, First of all, we have today, and we just use the Excel function today. That's easy. You could change it if you'd like. So our goal date, let's choose any goal we want. Let's change a new date. We can do it just for sake of something easy. Let's do December 31st of 2019. All right, and as you see there, the change in days has already updated to be relative to the previous maturity from the last time I ran the solver program. All right, so in the monthly expenses, here's an interesting component to this model is I have student loans in mind here. So if you have a monthly budget and you put in a number, that could be part of your planning for how you're going to facilitate repayment of these loans given your life circumstances. So before we get into economic optimization and marginal revenue, marginal cost, just as an interesting aside, whatever your budget is and the loan repayment schedule you desire, well, that's going to translate into a minimum salary after graduate school. So you can put in your effective tax rate below, which is typically around 23% for professional salaries before the executive level. And we're going to calculate the salary needed based on simple present value of the above inputs, discounted to, I'm sorry, not discounted, but amplified by the tax rate. So 1 minus the tax rate. If that's in the denominator, the salary will become larger to show you the gross salary, so before tax. And later on, I'd like to show you how I got the optimal solution by looking at the change between different payment periods to see the benefits and cost of how long it's going to take you to repay. So of course there'll be more interest, but there'll also be more cash flow available in the present. And so I set up a profit maximization equation for marginal revenue equals marginal cost. That is usually the definition of profit maximization. And it turns out that that's going to be repaid in about 1.5 years for the situation. But that's a more complex calculation. I have that below. But let's look at what this model can do. All right, so we put in a new goal, and let's change our monthly expenses to something different. So maybe 42.78. How about that? Let's keep the tax rate near there, but let's change it to 22%. All right. So a lot has not changed yet. The change in days is still the same. The payment has been determined from the last time we ran the solver. And before we do run the solver, let me discuss a little bit about this loan table below. So here we see again the 7 loans with the starting principal, and then in each cell we see the end of year balance. So the end of year 1 for that loan, the end of year 1 for that loan, and so forth. And on the far right, we see how much interest is calculated, and I have a very complex conditional statement above that's a lot's going on there, but essentially it has some internal logic that it finds where the payment stops and everything's paid off by using a very powerful combination of Excel functions, the match and offset function. If you don't know how to use those, I highly recommend looking them up. They can greatly empower your models to be able to work within the same column. So if you have that logic in there, there's no need to have another table somewhere else or to have it more cumbersome. It can figure it out for itself where the table's supposed to end. Okay, so then at the final bottom, we see how much is the total we paid, and that's uses quite a long equation up there, but don't be too scared of it. It's just looking up the details based on the name of the loan, so ABC, ABC, and then which column to pull data from. So that data gets pulled down there, and then a calculation is made so that we know the total amount of payments at the month previous to final repayment, and then we calculate the exact payment including the last month's interest to get a perfectly exact figure, rather than just multiplying the total number of months that payment is in process by the monthly payment. That would not be accurate. And so by simply subtracting the total paid from the principal, we can determine how much interest was paid over the repayment period. Okay, so let's get started and show you the solver Java applet, which is unfortunately not native to the Mac version of Microsoft Excel. In Windows, because the Windows architecture is very uniform, it is embedded in Excel, and you can enable it by turning on the data analysis pack and other options like that. So let me make that smaller, and let's bring up the solver program. So it usually shows up under Tools, and then at the bottom, Solver. This isn't going to come with normal prepackaged Microsoft Excel. You have to go to the internet, download this program, and install it. It's completely free. I think it's even open source, and it is very powerful. All right, and I apologize if it's a little small here. Something about the way Excel is rendering this Java program that's not native to itself comes out a little small. But basically what we want to do is make all that change in days 0. So all of these days should end at the same, and we'll know that's true if this box here is 0, which is the sum of this column G. So if all the loans end at the exact same time and all the numbers are positive and this is 0, well, that means that our mission has been accomplished and all the loans will finalize on the same day. So we put in some constraints. The first constraint is column D, the payments, Well, they have to be positive. We're paying the bank's not paying us, so we want to make sure those are non-negative values. So we set that column greater than or equal to 0. And here's another important thing. If you have covenants in your loan where there is a minimum payment stipulated and it can't just float around, yeah, this is the place to do that. So for example, on D5, this loan has a minimum contractual payment of $95.77. So you make sure that the solver program doesn't change that to be below. And the logic in the rest of the model will simply let that loan expire early if the case may be that the $95 will be too fast for it to end with the rest of the loans. And finally, as I mentioned before, column G, the change in days, well, those need to be equal to 0. That's kind of the point of the whole model, is that we want to keep changing that payment so that when we do the time value of money calculations, the maturity date changes until it equals our goal repayment date. And that's the most important constraint in this model. Again, the algorithm you use anytime you don't have anytime you have powers greater than 1 or less than 1, you need to use nonlinear because these are basically geometric sequences. So use nonlinear there. The other ones, of course, are simplex and evolutionary, but we don't need to talk about those right now. All right, let's give it a whirl and see if it can figure out what we should pay the banks. And depending on the speed of your computer, this could take quite a while. So don't be afraid of that. Then it gives you a little beep, and it looks like we're successful. So we'll go ahead and keep that solution. Press OK. Okay, so remember our goal was December 31st of 2019. Well, look at this. So all these have changed to 2019. And the change in days is the number of periods calculation. It's one of the built-in time value money equations in Excel. So that's how many days we'll be repaying. In the payments, you see how these are very long decimals. That comes out probably pretty small on your display. But these are exact calculations. The computer has, I think, 14 decimal points of resolution. So it's very accurate and very powerful. So these are the payments that we would make on each one of these loans. This whole set of unconsolidated loans with different interest rates. Here you see 7.9, 6.8, 2.875, and they're all different. So we need to adjust the payment periods to get all this zeroed and be successful and be debt-free in 2020. Okay, so let's look at what happened down at the loan table. As again described before, these are the ending principal balances at each year during the repayment period. So because that's the end of the year and we're paying it off in a little over 7 years, there will be payments in year 8, but the balance will be 0 at the end. So that requires a little bit of an additional calculation to figure out, well, how much interest did we pay and how much total money did we pay to the bank for year 8, which was a partial year. And so that's where this equation on the right came in, where there's built-in logic so that the formula in each one of these cells through I-17 through I-27 has built-in logic using the match and offset combination that tells it, well, what year did which year had final balances of principal, and that will tell it that, okay, this year, year 8 in this case, is the year it's being paid off, and so we can use a conditional statement to perform the different calculation, which will get us the exact amount of interest for that year. And if all worked correctly, we have the total paid, which is simply a sum of all the interest, and that should equal the sum horizontally of the total interest paid by simply subtracting the total payment from the original principal. So if these two are equal, we know we have an exact model and we have a very solid control about the quality of the data here. So I'm very confident that that is working properly. All right, the next component that I'd like to show you is based on this repayment scenario with a monthly budget of $4,200 and $78 and an effective payroll income tax rate of 22%, we can calculate the salary we need to pay for all of this repayment, and all of our monthly living expenses. And that turns out to be just shy of $80,000. Now, below, similar calculation to getting the gross salary above is the optimal solution. And this is a theoretical repayment plan that, as you see, this is a constant, and this itself is another solver solution. I'm not going to demonstrate all of that because it's fairly tedious, but below, what I did was I did theoretical point estimates, time to maturity of 10 years, 9 years, 8 years, and so forth, and figuring out from the computer, every time I ran solver, it would tell you the payment, the total monthly payment, that is for all 7 loans, and the interest, the total interest paid. So we have all these point estimates here, and that's starting to shape up into a kind of graph that we can extrapolate information from. The marginal cost, in this scenario, I determined that marginal cost would be the difference between the total interest. So, and that makes sense because there's a time value to money, and that is known as interest. So the difference between paying off in 10 years and 9 years is an additional interest payment to the banks of almost $3,000. So that's our point estimate for the marginal cost curve, which is merely the change or the slope of the total cost. And also we take an average of average yearly interest payment merely by dividing one into the other. So B35 here, the interest, divided by B33, the years. So the average yearly payment, it's very obvious on year 10, is $2,432. And that's important in economic decisions, especially for production decisions. I don't use it too much here, merely for demonstrate the size of the interest payment. But it's very important on production to be aware of your average variable cost. So that's the row 37. And marginal revenue, this was a little bit tricky, but basically I determined that for the change in value, that is the value to me, the loan holder, would be C34, so we see the payment, minus B34, so the payment changes, okay? So the interest is the cost or the time value of money, but our revenue in this situation, it's a little bit stretched from some traditional models of marginal revenue, but our revenue is the change in cash flow. So if our monthly payment shrinks because we have a longer debt repayment period, we basically get a benefit of an additional, in this case, $51 per month of money that was not mailed to the bank. So that's savings, that's economic profit. And the way we figure out the solution is figuring out where marginal cost and marginal revenue equal one another, and that will give us the time to maturity that should be our goal to repay our loans. Scrolling over a little bit here, that happens, interestingly enough, very, very soon. So we have, this was, again, marginal cost and marginal revenue. They equal each other somewhere about a third of the way through in the second year. So we can set up basically a very simple high-low type of equation, algebra 1, but lucky for us, using this computer, using Microsoft Excel, we have a program to save us a lot of head scratching, and that is the intercept function. So you can mainly set an intercept and put in the arrays. So we see the x-axis is the years, and the marginal cost, the interest payment, being on the y-axis. And Excel will tell us where the y-intercept is when we start, essentially, when time is 0. and that came out to be this number here on the y-axis. And similarly, we do the same thing for row 38 with marginal revenue. And again, the second part to any linear equation is, first of all, the intercept, that's the constant above. And the other one is the slope, or the rate of change. And again, Excel makes things wonderful for us by including a slope function. And we do it the same way by including two arrays inside the slope function, and we get an equation. So basically what we're looking at here is the marginal cost is equal to this constant, the y-intercept, plus 45 times the x-axis variable. So that's years. So we have this slope times the years. So that's the rate of increase of the interest payments over time. And here's where Excel really shines on these kind of economic profit models, is we can make that equation just like I described. So H41, the intercept, plus H42, that's slope, or M. Usually in textbooks they call it M, and that's times H44, which is going to be our X variable, or in this case a time variable. And our goal is for Excel to tell us, well, what time variable on the x-axis should we try so that those equations equal each other. And it will do that millions of calculations per second down to a resolution, again, of 14 decimal points. And great news for us, we don't have to set the things equal to each other or divide or anything like that. So we just run solver, and we set this as the target objective cell to be 0, and it'll tell us that the optimal number of periods is 1.3267, etc. So that's basically a fraction of a year, and that can be translated into months pretty easily by using round functions and separating the remainder and changing it to base 12. And when I did that earlier, the optimal monthly payment on the debt was $43,130, and that worked out to a salary needed of $115,000. So this is very interesting, and I think students especially will find this useful. That honestly was the reason I made this, viewers, but I hope you've enjoyed this presentation of how to optimize your multiple loans. Again, this is Matthew Nelson, signing out.